Hello everybody, and welcome back to another Eng 130 video tutorial. In this tutorial we're going to continue finding the internal forces at specific points along a beam. So nothing's going to change, but this beam that we're going to have today is going to have a little bit of a trick to it. It's going to be at a diagonal. And the diagonal is like the professor's go-to way to kind of screw students on the final. We always give you nice horizontal beams in the lab, and especially during lecture examples, but then when you come to the final and you have a diagonal beam, a lot of students start getting confused on what to do. But the process is actually the exact same as you would with a horizontal beam, and I'll show you that right now. So nothing really new here. Again, this whole week is going to be focused on internal forces at a point. So the video now and the video in the next video, they're going to be the same thing, but it's always good to practice, because remember, these concepts are going to come in handy next week when we start getting into bending and shear moment diagrams. So with that being said, let's begin. Alrighty, so looking at this example, it would like us to determine the internal normal force, shear force, and the moment or bending moment at points C and D. So we're going to do it at 2 points this time instead of just 1 point like we did last time. And as you'll see, the process is exactly the same, but again, it's good to have as much practice as possible. That's the only real way you kind of get good at these, is just practicing. So remember what I said last time. The only thing that's really going to get students in these examples is sign convention. Really, the only thing that you guys need to solve these problems is just equilibrium, and you guys are the experts of that already. So the only thing that we're going to have to remember for this week is just the sign convention when we cut a beam. So if we cut it on the right side over here, we're going to have a shear force that goes downwards. We're going to have a moment. Oh, let's draw a better moment than that. So we're going to have a moment, and remember, the arrow for a moment will always be pointing towards the top of the beam. And we're going to have a normal force which points away from the beam. So this right here, the moment we put as M, the normal force we put as N, and the shear force we put as V. And in my experience, you guys are usually good with the normal force and the moment. It's always easy to remember that the arrow points away for normal force and the arrow is at the top for the moment. It's usually just shear that confuses students. So remember, if you're cutting the beam on the right side, our shear will always go downwards. And we know that everything on the other side must be exactly opposite. So in this case, our shear is going to go up. Our moment will still have the arrow at the top because it's opposite, but it's nice and easy to remember. And we're going to have an axial force that points away from the beam. So again, this will be our moment, V, that's M, our shear, which will be V, and our normal force, which will be N. And that's all we need to solve for these problems. So again, it's just finding the support reactions, cutting the beam, and then finding those internal forces. So the first thing that we're going to need to do, of course, is a free body diagram, because we always need to do one of those if we're solving for support reactions. If you guys were to just take your pencil or pen and write on the diagram, oh, I guess I shouldn't go in black because it's very hard to see. So if you guys were just to go right on your exam paper and draw something like this, I hate to tell you, but you're not going to get any full marks at all. This does not count as a free body diagram. You guys actually have to draw one by yourselves, which kind of sucks, but it is what it is. So for this beam, what I'm going to do is, this one's diagonal, so it's going to be a little bit more challenging for me, at least. I know that some of you artists are going to be really good at it. So we're gonna, what I'm going to do is I'm just gonna draw, I'm gonna kind of cheat and just draw two beams, and I'm gonna move one of them to make it diagonal. So yes, this is cheating for me, but I don't care. Whatever makes my life easier. So like this, and oh, I guess I didn't think ahead. I have no idea how to rotate this. Alrighty. So new plan. Since I don't know how to rotate it, I'm gonna draw it. Alright, so we're going to get rid of that, and I'm just going to draw the second one by myself. So that's not what I was looking for. Let's try again, and I can move this at least. Alright, so I can put it like this. Not the best, but this will work. This will be just fine for what I'm trying to do. And let's actually just move both of these over to the side so I have a little bit extra room. So perfect. So let's say that this is the beam. Probably not the best representation, but perfectly fine. So if we look, the first thing that we're going to add to this is our external loads. So we have a distributed load that acts along the horizontal span of the beam. So I'm just going to kind of draw the silhouette of what that would be. So we know it's rectangular, and that'll have a force right at the center. And this force right now I'm just going to call F1. We'll find that out in a couple seconds. And we know that this has a magnitude of 2 kilonewtons per meter. We can also draw our support reaction. So over at B, we have a roller, just like this. So this one's going to be B. And so I'm going to call it BY because it's vertical. And then at the pin, what we can do is we can draw our forces any way we want for a pin, as long as our two forces are perpendicular to each other. So I know a lot of people would like to do this. And this is completely fine if you do it like this. It's just going to make the analysis a bit more tricky in my head. So what I'm going to do to make my life a little bit easier is I'm going to draw it like this. And it's perfectly fine as long as they're still perpendicular. So if I draw them like this, those two forces are still perpendicular, I'm good to go. And this is at A, so we can call this AX. And this one can be AY. And finally, it's always good to put in all the dimensions of the beam. So we know that the horizontal span is split up into two. So we're going to have 3 meters and 3 meters. And the reason why is because at this point right here, we have point D, which we're going to put in there. It's good to show point D because we're going to need it later. And we also have a second point on the beam, point C. So if we're measuring this direction, we see that this one's kind of split in two as well, where we have 2 meters, and our last one's going to be 4 meters. And this point right here is going to be point C. And what we'll do is we're going to find the internal forces at both of those points. So one other thing real quick, we can also put in, and I'm just going to draw this in a different color so it stands out, that the angle of incline of this beam is going to be 45 degrees. So just take a quick look at the diagram, quick look at our free body diagram. Seems like we're good to go. So I'm going to come down here, and the first thing I'm going to do is the support reactions. So right here I'm just going to put support reactions. Support reactions. I know I'm a slow speller, so bear with me. And in the end, I'm going to have to analyze point C. So I'm going to have to draw a cut at point C somewhere, so I'm going to have to cut there. I'm also going to have to analyze point D. So at some point, I'm going to have to cut right there as well. And if I'm looking at this and picking which sides to do, well, for part C, I think that the best side is probably the smallest side. So for C, I'm going to analyze this half. So I'm going to need to find AX and AY. Looking at D, I think that this half would actually be simpler. So I'm going to have to find BY as well. So in this case, I'm going to have to find all the support reactions. So that's what I'm going to do. So the first thing I need to do real quick is find out what F1 is. So we know that F1 is 2 kilonewtons per meter, and that acts over a distance of 6 meters. So F1 is going to be 12 kilonewtons. So that was probably nice and easy. Now we can go to maybe what's perhaps the more fun stuff. And that right here is going to be summing the moments at the pin, because I want to get rid of AX and AY because I don't know what either one of those are. So I'm going to go sum of the moments at A is equal to 0. If I do this equation, what I'm going to find is I'm going to need a horizontal distance. Right now I have its diagonal distance, but what I'm going to need in blue here is this distance right here. But that's actually really easy to find because we know that this is just going to be 6. So the hypotenuse length times cosine of the angle, which is 45. So just like that. So now when I'm starting to do my sum of the moments, I can start figuring everything out. So we see that there's going to be a BY component. So we're going to have BY, and its distance is going to be the 6 cosine 45. And we have to add the other 6 meters about the horizontal beam to get there. Now, if we check the rotation, what we find is B creates a counterclockwise moment, so we're good to go. BY is good. Next, we have F1. So we know we have F1. And actually, we're just going to substitute F1. I don't know why I wrote F1. We know F1 is 12. And then its distance is going to be the 6 cosine 45. But instead of plusing 6, we're only adding 3 meters to this one. And we see that this is going to create a clockwise rotation, so this one's going to be negative. And of course, all of this is equal to 0. So we just have two forces. Actually, not too bad. It's pretty simple. So when we solve, what we find is that BY is equal to 8.485 kilonewtons. and it's a positive answer, so our assumed direction of up is correct. And again, just to make this easier to find later on, I'm just going to highlight it real quick so we can easily find it later on. Because remember, the goal of these isn't to find the support reactions, it's to find the internal forces. So By is not my answer, but I will need it later. So if I look up here, a nice trivial one is going to be sum of the forces in x. So if I were to go sum of the forces in the x direction is equal to 0, well, I'll have ax, as we all know. But if we look up, there's nothing else in the x direction. So from here, we can conclude that ax is equal to 0 kilonewtons. So again, nice and easy and trivial. Ax is equal to 0. So our last one that we can use to find ay is just going to be sum of the forces in the y direction is equal to 0. So looking at my equation, I had ay going up. If I look, I got F1, which is 12 kilonewtons, acting downwards. So minus 12. And then we had By acting upwards, and we know By is 8.485. So then we're going to go plus 8.485. And all this is equal to 0. So therefore we can solve, and we find ay, I forgot my therefore, ay is equal to 3.515 kilonewtons. And it's also going upwards because we got a positive answer, so our assumed direction was correct. So those are the support reactions. You guys should already know how to solve these. This should be nothing new, and this should hopefully be the easy part. So now we can go on to the actual question. Determine the normal force, shear force, and moment at points C and D. So let's start with C first. So point C. And if I look on my diagram, I said that I'm going to analyze that purple part at C. So to find those internal forces, what we need to do is cut the beam. Whenever you cut a beam, you expose its internal forces. So coming down here, I'm going to go, let's go point C. So we're not analyzing point C. I guess we are analyzing point C. So this just tells us what exactly we're doing. And we know that we cut the beam something like this. And I'm going to, what should I do to make this a little bit easier? Let's move this more to the center. Alrighty. So we know that at this beam we had that's actually very, very steep. Oops. Like this. Oop, I don't know why that's stuck like that. Alright. Erase it. Okay, there we go. Alright, round 2. So I'm going to try and more have a 45-degree angle, and this still seems extremely steep. Alright, one more time. And if I can do it now, then we'll just leave it. Technical difficulties on my part. Okay, that looks much better. Alright, perfect. So this will be our beam. What I'm going to do is I'm just going to move it up a bit. And we know that we had support reactions at A. So on this side, we had a force coming straight up. And this force was the 3.515 kilonewtons. 3.515 kilonewtons. And then we cut the beam. So what that means is we have to replace everything at this cut right here by its internal forces. So if we look at our little diagram, we cut it on the right side. So we're going to have this side over here. So we're going to add in all of those internal forces. So our shear on the side will be going downwards, which we'll call VC. We'll have a bending moment like this, which will have MC. And we'll have, of course, a normal force coming straight out. So I'm going to try and actually put this more towards the center. Still not the best, but it'll do. And we have N sub C. So just like before, we're also going to have to dimension this. So we know that this right here is going to be 2 meters. Here to here is 2 meters. And we're good. Everything that we want is on this free body diagram. I'm just going to put in the points real quick. So we got A at the top, C at the bottom. And we have 3 equations. We have 3 unknowns. Therefore, we can solve for absolutely everything. But now things get a little bit tricky because everything's at a diagonal. And that's where things start to kind of really suck. Things get at a diagonal, things suck. So what I recommend for this case is switching our axis. Whenever you have a diagonal beam, this isn't all the time, but it's usually beneficial to change our axis to go along with the beam so we can treat it more as a normal scenario. So if I take my axis and I make this my new axis, so the X is going to run parallel with the beam like this, and I'm going to call this x prime, and I'm going to call this one y prime. Well, now, if we rotate everything, we'll see that this is actually the exact same as a normal beam with just a diagonal load. And this diagonal load, we already know, is acting at 45 degrees. So now our lives just became a lot easier in this case. Because now what we can do is we can go sum of the forces in x prime equals 0. So remember, when we're solving for internal forces, it doesn't matter which equation you start with because each one is in their own domain. You'll never have one equation with two unknowns. So we can start with sum of the force in x prime equals 0. So from here, what we find is that we have NC going to the right, so we have NC positive, and then we have the 3.15 going to the left, so minus 3.515. But we're only going to take a component of that one because now this acts at a diagonal. We're only going to take a component. So in this case, we're going to times it by sine of 45. And we know all of this, of course, is equal to 0. So I can put equal 0. And when I solve, I get NC is equal to 2.49 kilonewtons. So remember, nice thing about internal forces, I don't have to say compression, I don't have to say tension, I don't have to change any signs. Whatever answer you get, that's your answer, you're good to go. So now I can go down, I go, okay, well I did some of the forces in x, let's do some of the forces in y. So some of the forces in y prime is equal to 0. In this case we have a shear going downwards. We're going to have minus VC, and then we have the 3.515 going upwards. So plus 3.515. And we know that only a component of it is going vertically, so we're going to multiply by cosine 45. And we know that all of this is equal to 0. So therefore, our VC, our shear at C, is equal to 2.49 kilonewtons as well. And it makes sense because cosine and sine of 45, they're the exact same thing. It's what we expect. So over here, what I'm going to do is I'm just going to box this. This is an answer. We're good to go. So we're already done 2 out of the 3. Our last one, of course, is going to be summation of the moments. So remember, sum of the moments, for these type of things, I always like to take it about where I cut. So in this case, I'm going to go sum of the moments at C is equal to 0. And from this equation, I'm going to move this down a bit because these usually get pretty long when you're dealing with distances. The first thing that we have is MC, and that's going counterclockwise. So that's a nice easy one. We're going to have MC. And if we look to the other side, what this is going to split into is the 3.515. So we know that we're going to have the 3.515, and only the vertical component of that is going to create a moment. So we're going to multiply that by cosine of 45. So this right here is just the force. First bracket is just the force, and the distance now is 2 meters. So from here, we're going to multiply all that by 2 meters, and this is equal to 0. And real quick, we see if it's a vertical component, it's going to start creating a clockwise rotation. So this is going to be minus. So MC minus this is equal to 0. Therefore, MC is going to be equal to 4.97 kilonewton meters. So right here, I can highlight this, 4.97 kilonewton meters, and that box didn't turn out too bad. So there's our internal forces at point C. But we're not done yet because the question says, okay, well, it wants it at point C, check, but now I would like it at point D as well. And this will kind of allude to what we're going to start learning next week in bending and shear moment diagrams, is that the internal forces, depending on where the point is, they change. And in engineering, of course, we're going to want to know where the maximum is. So we're going to find out where to find these points when they're maximum or minimum, stuff like that. So looking at D, what we said is, okay, well, we're going to analyze the right-hand side because it has less going on. I don't want to analyze the left-hand side because I'm going to have to include the diagonal, everything like that. That's just too much work. I don't want a lot of work. I want nice and easy. So if I cut the beam at D and analyze the right side, it's going to look something like this. So first thing first, we're going to go, oops, I was going to say joint, but we're so done trusses. So we're going to put point, not joint, point D. And if we cut, we're going to just have a nice horizontal beam. So something like this. We know on the very right hand side we have a By reaction. So right here we have By. And we already know that By, looking up here, is 8.485 kilonewtons upwards. 8.485 kilonewtons. And then we have, I don't know what I was doing there. Oops, I erased too much. Kilonewtons. I know that I have a distributed load that acts across this. So I'm just going to draw the silhouette of the load. If I can draw correctly, this looks kind of terrible. I'm going to erase it. You guys deserve better than this. You guys, all right, here we go. Hopefully this will work out a lot better now. So we're going to have a distributed load that comes right across. So something like this. Perfect. So this will still be 2 kilonewtons per meter. That doesn't change. And then, of course, we cut the beam on the left side. So on the left side, we're going to have to replace this with all of our forces. So on the left side, start with the easy ones. Remember, the normal force will always be pointed away. So we're going to have ND. We have a bending moment, and the arrow will always be at the top. So this one will be MD. And finally, we have shear. And shear, if we're analyzing the right side and cut it on the left side, the shear is going to go upwards. That's going to be VD. I'm going to put the points in real quick so we know where everything is. Excuse me. And then finally, I'm just going to add an arrow, which I'm going to call F2, which would be our new force caused by that distributed load. So this one's going to be F2. And that's it. We have everything. Oh, except dimension. So remember, we always need to put a dimension. And we know that point D is located at 3 meters from the right. So from right here, put 3 meters. So from here, we start solving everything. But before we do, we need to solve for F2. But that's really simple. We know that F2 is going to be equal to the area of that distributed load. So it's going to be the 2 kilonewton meters times by 3. So we know this is going to be 6 kilonewtons. All right, perfect. So now we can go anywhere we want. So last time we did some of the forces in X, some of the forces in Y, and some of the moments. Let's switch it up this time. Let's go some of the moments. And again, always about the cut. That's the best place. So some of the moments at D, it's equal to 0. Well, from here I got MD, but it's going it's going clockwise. So we're going to have minus MD, and we're going to have F2 also creating a clockwise, so negative moment. So minus F2, which is 6. And this acts halfway across the beam, which is going to be 1.5 meters. And then finally, we have By creating a counterclockwise rotation, so plus 8.485. And that's at the other side of the beam, so 3 meters. And all this is equal to 0. So from there, our only unknown is MD. We can see that MD is going to be equal to 16.5 kilonewtons times meter. I'm just going to highlight this in red real quick because this is a final answer. So remember, please box your answers. It was actually in the midterm where it says please box all of your answers, and some people still didn't box their answers, but I know that wasn't my section, so shout out to section G because I know you guys did. Or at least I hope you guys did. You guys probably didn't, and now I'm talking bad things about the other section, and it's probably not even true. Alright, so now we can go sum of the forces in X equals 0, and this one's very, very simple, because if we look up, we have ND going to the left, so our equation would be minus ND, and if we check, well, that's it. So therefore ND, negative ND must be equal to 0, so therefore ND is equal to 0 kilonewtons, and I can box that as well. All right, perfect. So our final one is going to be summation of the forces in the y direction is equal to 0. So from here, again, it's very, very simple. We have our shear, and our shear is going up this time, so we're going to have VD. And we have F1 going, or sorry, F2 going downwards, so minus 6. And then we have By going upwards, so plus the 8 point, well, what was it, 485. and all this is equal to 0. So therefore, VD must be equal to negative 2.49 kilonewtons. And this is the best example in this case because it's our first negative. So remember, if you guys get a negative, don't change it. Don't put in compression. Don't change anything. Just state your final answer is VD is equal to negative 2.49 kilonewtons. And that's it. There's our internal forces at this point. So one thing I just want to show you guys before we end this video is just look at the internal forces at point C. Look at the internal forces at point D. They're completely different. And now I'm going to ask you guys, okay, well, we figure out the internal forces at 2 points. So let's go to a fun color just to end the video. So we found it at this point, and then we also found it at point C. And we found that the moment at point D is much larger than point C. But is it the maximum moment on this beam? Well, it might be, but probably not. So what you guys will see next week, as I said, this is kind of just an introduction to the real stuff, which is next week, is we're going to start to learn how to find the moment and shear at every point in the beam. And it's going to be a little tricky at first, but you guys are going to realize that there's some nice relations that make it solve very, very quickly, very, very easily. But for now, all we're focused on is finding them at a point. And the only thing that you guys are really going to have to know this week that's going to be important is this right here. Just our sign convention. If you guys remember that sign convention, you guys are good for this week. That's the only thing you need to know. You cut a beam, you get those forces. That's it. You guys know that. You're good. Next week, we're going to take it a step further and discuss everything you guys will need to know for the exam. So that concludes this video. Thank you guys all so much for watching, and I'll see you guys in the next video.